polynomial long division. Consider the following example. X plus 2 in brackets multiplied by x plus 3 in brackets is equal to x squared plus 5x plus 6 when expanded. Let's reverse this process. If we start off with the product, x squared plus 5x plus 6, and then divide it by one of the factors, so I chose x plus 3, that equals x plus 2. Now polynomials behave like integers when multiplied or divided. And before we go into the mechanics of polynomial long division, let's have a look at an example of long division involving integers. Find 197 divided by 6 using long division. And the process goes something like this. And you may have seen this before, some time ago. So this is an opportunity to reacquaint yourself with this process. The dividend goes here, the divisor goes here, and then we start. 6 into 9, well 6 into 1 we cannot do, so we consider the 19. So 6 into 19 goes 3 whole times. 6 times 3 is 18. We place the 18 just under the 19 there. 19 minus 18 is 1. Now 6 into 1 we cannot do, but we have this 7 in reserve. We can drop that down so it's written next to the 1, and then we treat that as 17. 6 into 17 goes 2 whole times. 6 times 2 is 12. Then we do 17 minus 12, and that gives us 5. And then we try and repeat the process again. But 6 into 5 we cannot do since the divisor is greater than the remainder, and then the process stops there. So the result is a quotient of 32 with a remainder of 5. So looking at it, I guess, a different way, this can be written as 197 divided by 6 is equal to 32 and 5/6. But sometimes we like to write it in a form that does not involve fractions, so not involving this 5/6. So can we write it a different way? Yes, we can. So if we multiplied every one of these terms by 6, so this 197 divided by 6 is the same as 197 over 6. Multiply that by 6. Multiply the 32 by 6 and the 5/6 by 6. You end up with 197 is equal to 6 times 32 plus 5. So this is in the form a dividend equals divisor multiplied by quotient plus remainder. And notice no fractions used here to express this result. Also note, and I've kind of made this point sort of before when I was looking at this process of long division, that the remainder is less than the divisor. Because if it's not, then it's not a remainder. We can still divide it. So just more formally, let P, the dividend, and D, the divisor, be integers with D greater than or equal to 1. So this is the divisor, sort of, it has to be at least 1 integer. Then there are unique integers, Q, so that's the quotient, and R, the remainder, such that P, the dividend, is equal to D times Q, so that's the divisor times the quotient plus some remainder, where the remainder has to be greater than or equal to 0. Yes, we can have a remainder of 0, but it has to be less than the dividend. Now, an interesting thing happens when the remainder is 0. So when the remainder is 0, so let's say you took an integer and you divided it by some divisor, and then you ended up with a remainder of 0, then what does that mean? That means then that the divisor D is a factor of P, such that P is equal to D times Q, or plus 0, but we don't show the plus 0. So as an example, 20 divided by 4, well, we know that's 5 with a remainder of 0. So what does that mean? That means that 4 is a factor of 20.